Alright, in this lesson we're going to review finding various volumes of rotational solids. We're going to start with some simple ones, some disk method style solids. We'll start with example 1, find the volume of the solid generated by revolving the region bounded by the curve, forgot a y there, curve y equals x squared, the x-axis, and the lines x equals 2 and x equals 5 around the x-axis. So if you think about what we've got going on here, we've got the curve y equals x squared. We've got the lines x equals 2 and x equals 5, and the x-axis bounding this region. We're going to revolve it around the x-axis, so it's going to be a disc-shaped solid. So we're going to find the volume by taking pi times the integral from the left-hand side of the region to the right-hand side, since we're revolving around the x-axis. So we've got the integral from 2 to 5, and my radius is the distance between this curve and the x-axis, which is the equation of the curve. So we're going to take that and we're going to square it. And that's going to be the integral that we use to find the volume of this solid. I can opt to either do this on the calculator or by hand. I'm going to go ahead and use the calculator. So I've got pi times integral of x to the 4th, since that's x squared squared, with respect to x, from 2 to 5. And that's going to give me 1,943.389. Alright. Example 2, we're going to find the volume of the solid generated by revolving the region bounded by x equals the natural log of y, which is going to look something like, ooh, yeah, that's that's y equals e to the x. The y-axis and the lines y equals 2 and y equals 7. So we're taking this region right here, and we're revolving it now around the y-axis. So we want everything in our integral to be in terms of y. The limits of integration are going to be in terms of y. The radius is going to be a function of y. So we've got pi times the integral from one end to the other, so from 2 to 7, from the bottom to the top. And my radius is going to be the distance from the axis over to the curve natural log of y. So my integrand is going to be the radius squared with respect to y. And I'm going to go ahead again and calculate this on my calculator. So I've got pi times the integral of quantity, natural log, and again my calculator is going to use x. That whole quantity squared. Make sure you square the whole quantity and not just the x. From 2 to 7. And we end up with an area of a volume of 34.793. Alright, so those are two disk-based solids to find the volumes of. Let's go on to washer-based solids, and if you look at the lesson, there's a lot of review description of how we use the washer method and some pictures and stuff like that. We're going to skip right ahead to these examples. Example 3, we're going to find the volume of the solid generated by revolving the region bounded by these two curves around the x-axis. So I'm going to go ahead and graph those two curves. Except I better go to my graph screen first. So we've got y equals x squared plus 4. And we've got y equals negative 1/2 x plus 5. And then I'm going to go ahead and look at the graph of this. Make sure I'm in the standard window. So I graph those two curves. And there's what the curves look like. So we've got a parabola, a line like this, and we're finding the volume of the solid generated by this region when we're revolving around the x-axis. Okay, so we'll set this up we've got pi times the integral. Now I need my limits of integration, and they're going to be the left endpoint x coordinate and the right endpoint's x coordinate. I'm going to go ahead and find those on my calculator. So we'll find the intersection points. Negative 1.280776. And the other intersection point. Roll over and find that. And that's 0.780776. And now I need my integrand, and my integrand is going to be the radius formed by the outer boundary of the region when revolving around the axis. And then I have another inner radius, and I'm going to subtract those two. So first, the radius, the outer radius, is the distance from this curve down to the axis. And that's just the value of that particular function at that time. So that's the line, negative 1/2 x plus 5 quantity squared. And then my inner radius is the distance from the parabola to the x-axis. And that's going to be x squared plus 4. Square that. And now I'm going to go ahead and find the value of that integral. And we've got pi times the integral of the quantity negative 1/2 x plus 5 quantity squared minus quantity x squared plus 4 quantity squared with respect to x from negative 1.280776 to 0.780776, and we get 43.123 for the volume of this solid. Alright, example 4, we're going to do the same thing, except this time we're going around the y-axis. And I can't really graph these functions on my calculator, but realize that I can graph the inverses of these functions and treat it like I'm revolving around the x-axis and find the information accordingly in order to set up our integral. And that's, frequently helpful. So I'm going to go in here and I'm going to graph the inverses of these functions. I'm going to graph y equals sine of x plus 4. Oops, this is my plus sign. And y equals negative x squared plus 7. And this is a handy trick to help me find the limits of integration and which curve forms the outer radius and inner radius, etc. When I graph these on my graphing calculator, all I'm doing is taking the inverse. So I'm going to gather the information by comparing it to the x-axis in these. So I go ahead and I look at the graph. And the parabola forms my outer boundary, and so my outer radius is going to be from the parabola. So negative y squared plus 7 quantity squared. And my inner radius is going to be from the trigonometric, so that's going to be sine y plus 4 quantity squared. And now I need my limits of integration. And so I go ahead and calculate those by finding the intersection points. Now, normally if I had graphed this by hand, I would want the y coordinates of the intersection points as my limits of integration. But since I graphed the inverse on my calculator, I want the x coordinates That's negative 1.97932. And the other intersection point is over here, 1.418. 3101. And there's my setup that I'm going to use to find the volume of this solid. And so I'm going to go ahead and calculate that. So I've got pi times the integral of the quantity. And again, when I type this into my calculator, come on, x, there you go. I'm going to have x's inside my integrand because my calculator just automatically uses x as its variable. Sine of x, make sure you close that parenthesis on the sine function. And the limits of integration. We get 227.549 for the volume. Now realize we looked at the inverse on our graph. What this region actually looks like is we've got this curve, and then we've got a sine function. Did I just put a cosine? I did just put a cosine function in there. We've got a sine function. Okay. Got a sine function, and we've got the parabola that looks like this. And so this is actually the region that we're finding, and all of the information that we get corresponds to that. The y coordinate of this intersection point on this graph is negative 1.979. The y coordinate of this one is 1.418. The radius is the distance from the parabola to the y-axis, and the inner radius is the distance from the sine function to the y-axis. Alright, so that's a little trick and tip we can use to help us when we're finding regions that aren't easy to graph, where we've got functions x as a function of y. Alright, that's it for our review on disk and washer based solids and finding their volumes. I'll see you next time when we start to rotate things around non-axes. Have a great rest of your day.